quantum communication, quantum key distribution. Okay, how one can do this trusted node satellite based quantum communication or untrusted node satellite based quantum communication, how how this QKT provides security to the communication. Okay, all those things we have talked about. What are the quantum mechanical principles involved there? We talked about superposition state, entangled states, and all those things. Okay. Now we'll see how we implement it to the lab and the field. Okay. Both lab and field, both how to it is implemented. Part of the equipment, what are the resources which are used there. Okay. So we talked of weak coherent pulses. For prepare and measure base protocols, they use weak coherent pulses or coherent weak pulses, whatever you say, or single photon source. Both are used for prepare and measure quantum key distribution protocols. And then you use entangled photons. So how do you make weak coherent pulses? Um, you take a laser. Laser is a coherent source of light. Okay, so you take a pulse laser. We are talking of pulses. Okay, so you take a pulse laser and you reduce the intensity. Okay, that's how you weak. So it's become weak coherent pulse laser, and you attenuate in such a way. It's a pulse. You attenuate it in such a way that on average per pulse is having not more than one photon. So you have prepared an approximate source of single photon. Okay, it's an approximate source of single photon. It's not a single photon source, although there is confusion. Okay, whether it is single photon source or it's not a single photon source, but it's not a single photon source. Why? Because laser is having different kind of photon distribution, and just by reducing the intensity you can't change the photon distribution. While single photon source, when you say, it has a completely different photon distribution compared to lasers. Okay, and that can verify, you can measure experimentally and you can verify whether this photon distribution, it follows single photon source or it follows laser, weak attenuated laser. This attenuated laser, these lasers follow Poissonian distribution, while this weak current pulses, they follow sub-Poissonian. They show anti-bunching, while this lasers show, they don't show any bunching or anti-bunching. They show Poissonian distribution. So by studying this photon distribution experimentally, you can verify whether the light is coming from laser or attenuated laser, or coming from single photon source. Okay, this signal is coming from single photon source, or this signal is coming from attenuated pulse laser. When we say single photon source, what does it mean? It's mean probability of getting two photons at the same time is zero, ideally zero, but when you do the implementation, when you make this kind of source, it won't be ideally zero, but probability of getting two photons at the same time should be very, very small. So that kind of source is called, means at a time there is only one photon. Okay, so a stream of photons is not just one photon comes and then there is no photon. It's a stream of photons, but at a time there is only one photon. Probability of getting two photons at the same time is almost zero. So that kind of source is called single photon source, and it shows, when you study experimentally, it shows anti-bunching. Okay, anti-bunching means one photon is there, so another photon cannot come. Okay, that's called anti-bunching. So two cannot come together. That's called anti-bunching. And how do you make this kind of single photon source or entangled photon source? I told you how you make this peak current pulses. Okay. Um, how you make this single photon source and entangled photon source? For that, you use lasers and nonlinear crystals. Here, this is a Chi2 second crystal, and you pump with laser. So one photon of the laser, okay, gets converted into two photons. Okay, and this process is called spontaneous parametric down conversion. Parametric down conversion. Down conversion means energy of higher energy is being um, converted to lower energy photons. This process conserves energy and momentum. This physical principles, okay, they follow. So one photon, higher energy, 405 nanometer. Here, this laser is blue laser, 405 nanometer. It's converting two photons of 810 nanometer, lower energy, higher wavelength, lower energy. And if you and these two photons are produced simultaneously. This pair of photons, they are produced simultaneously. So if you measure one photon, so you it ensures that another photon is there, okay, because they are coming together, they are generated together. One is there means another is also there. So this kind of source is called heralded single photon source, because presence of one heralds the presence of another, or detection of one photon heralds the presence of another photon. So that's how. And then you do the photon distribution of this light or this signal, and these are called signal and idler. So this signal, you do the photon distribution to verify that probability of getting two photons at the same time is very small. And what is entangled photon source? These two photons are coming together, okay, and you measure the correlation for a particular variable. Suppose you are measuring correlation, whether polarization of one photon is correlated with polarization of another, or whether orbital angular momentum of one photon is correlated with orbital momentum of another photon, or whether their time will, like time of arrival, are correlated, or their position and momentum is having correlated. So once we measure and see that they are correlated, so we say they are entangled photons. And without measurement, we can't say whether they are entangled or not. One will have to measure and show that they are correlated in this particular variable. So in that particular variable, they are correlated or they are entangled, not in other variables which we have not measured. So that's the entangled photon. We'll see how we produce entangled photons in the lab. And since this is light or photon, you need optical fiber that I have been telling you, and free space. So it can propagate both. For transmission, you can use free space or fiber. Then you need detectors. Here, this is the source. Okay, you are preparing these quantum states using these techniques. Weak coherent pulses, heralded single photon, entangled photon. These are the quantum sources. When it comes to detectors, you have single photon detectors. Okay, and one can have avalanche photodiode based single photon detectors, as well as superconducting nanowire single photon detectors. This avalanche photodiode based single photon detectors, they are very compact. They are not very expensive, although expensive, but not very expensive. While this superconducting nanowire single photon detector, because it uses the principle of superconductivity, you need like cooling, okay, cryostats, okay, to circulate the helium. So they use cryostats, and you have to circulate that. So you need this pumps and, okay, vacuum and all. So it becomes bulky and costly also. So that is the, but it has had detection efficiency compared to this APD based single photon detectors. Although it's costly and bulky, but it has higher detection efficiency compared to these APDs. And certainly, we will see the experiment. We need a lot of optical components to implement this quantum key distribution. So let's discuss BB84 protocol, one of the most popular quantum key distribution protocols. Here you are randomly is very important. So you are preparing randomly these photons in correlation states. This dice indicates that random preparation is being done, sometimes horizontal, vertical, diagonal, anti-diagonal, and then assign a bit. Okay, you can assign label, like you can label horizontal as 0, vertical as 1, diagonal as D, anti-diagonal as 1. Okay, so you can assign. And now after preparation, this prepare and measure, we are talking of prepare and measure protocol, and this is the most popular and the initial protocol. So after preparing this photons in polation state, you send it to the other part. We are calling it Bob, the other part. And again, Bob, this dice again is there. So randomly select these two bases. Okay, I talked of this basis. This is horizontal vertical linear basis, and this is diagonal basis, diagonal and anti-diagonal. Okay, so Bob selects randomly selects the basis and does the measurement. Okay, so this is the polation states bit assigned. Now Bob is making the choice of the basis, horizontal, vertical, linear basis, diagonal, and diagonal basis. If both are having the same basis, like you see, Bob Alice is sending this diagonal, and Bob is selecting diagonal basis. Okay, for measurement, they will have key. Same way, if Alice is sending V and Bob is selecting same linear basis, HV basis, and makes the measurement, they will have key. Okay, so that's how they develop the key. And once they have this kind of key, they do further error correction and privacy amplification. Okay, up to here, this quantum mechanics is involved: preparation of quantum states, their transmission and measurement. So up to this stage, there is quantum mechanical principles. Beyond this, you use classical communication protocols for error correction and privacy amplification. And after this error correction and privacy amplification, you will have secure key. Okay, this is called shifted key. And after this error correction and privacy amplification, you will have secure key. So you may say from where this error is coming. Okay, um, you can have like horizontal and vertical both. Okay, but here HV. Suppose Elise sent H and Bob has taken HV basis. It is giving key, but Elise has sent H, but Bob is measuring V. So that's the error. On the way, this polation has rotated. Okay, both are using same basis for preparation measurement, but Bob is getting wrong result. So that kind of result are discarded. So that is error because on the way somehow or Eve might have tried to rotate the basis. So that is like error. So that kind of error you do the correction protocols. Um, okay, do the error correction. As I told you, when we are using weak coherent pulses, so lasers are Poissonian source. You have attenuated them so that on average there is not more than one photon per pulse. But because of being lasers, Poissonian distribution of photons for lasers, still there will be certain probability that few pulses will have more than one photons, two or three photons. Okay, few pulses will have. You can't make it zero because laser uh, photons coming out of laser they follow Poissonian distribution. So because some pulses will have more than one photons, two or three photons, what this can be utilized for attacks. These are called photon number splitting attack. Some pulses EVs. So this attack is being done by Eve. Attacker is called Eve here in this cryptography terminology. So Eve is measuring like storing, taking, intercepting all the taking all the photons, okay, and making measurements on them. And when pulse is having two photons, after making measurement, Eve transmits one of the photons. If there are three photons, makes measurement and transmit like one photon again. Again, if there are four photons, Eve makes measurement and transmit one photon. So Bob thinks there is attenuation. As we talk, attenuation is not normal in quantum channel, but Eve can have all the information when they like communicate which kind of basis they have selected, how they have prepared, and Eve can listen because that is classical communication. This basis reconciliation, we call basis reconciliation, which kind of basis they have selected for preparation and measurement. So during that, that is done through classical channel. Okay. So Bob, Eve, this attacker or hacker can have all the information which basis, and they will have Eve will have information about the key. So this is very serious attack when you are using weak current pulses and photon number split attack. To avoid that attack, there is another protocol, very popular protocol, decay state protocol. Okay, so you send some decay pulses. Decay pulses, if you have seen VIPs like Karma, so there will be decay vehicles coming along with VVIP vehicle. Okay, for security. So you can't make out which vehicle is being used by this VVIP. The same way, you will have decay pulses along with the pulses which you intend to communicate the information. And then Alice randomly sends signal or decay state with fixed clock frequency to Bob. And Bob doesn't know when this decay is coming, when this signal is coming, real signal is coming. So Bob makes randomly measurements on the records the measurement, okay, or makes measurement. Then, as I told you, they do the classical communication, pub- publicly announce which kind of basis they have selected, and Bob computes the signal in the chi state with transmission probability per channel. What will be the transmission probability? And because randomly they are coming, so transmission probability should be same for both. If there is some because Bob is not knowing when decay is coming, when signal is coming, so transmission probability for both descent probability should be same for both signal and decay at Bob's end. If there is some like for one decay or signal, there is more or less, matlab, either one probability is more or less, then it ensures that indicates that there is Eve sitting there and making measurements. If it is not same transmission probability. So that's how decay ensures the security of your signal pulse. So here we show the implementation of a BB84 protocol. So you have Alice preparing correlation states randomly, and this how it is done. We will discuss in here. This is electronics to generate a random number, and time information is very important to record the time information. We use time tagger or time to digital converter. Okay, and so you send for sending you use launching optics, and then here you collect the signal and do the correlation measurement, and then you detect the photons using single photon modules or single photon detectors, and when the photon arrives you record the time. This time tagging is very important to ensure that what photon Alice is sending you are measuring that photon only, not any other photon, stray photons. And this time information, and when this photon was produced, okay, are sent, and when it was received, that information is communicated to classical chip. So that's how you implement this quantum key distribution protocol either in lab or field. We will see what is the difference between lab and field. Okay, so this is the field implementation of quantum key distribution ambiguity 4. So what you do, you have this reference laser, a beacon laser we call. Okay, so here you are preparing this correlation states randomly, and this what it does. This is electronics FPGA, field programmable gated array device. So it gives random voltage pulses to switch on or switch off these laser diodes. And in front of laser diodes, you have polarization optics to prepare the polarization state. Because these are being switched randomly, so these polarization states are being produced randomly. Okay, this is half a plate. Half a plate, what it does, so it rotates the polarization. So if linear polarization is coming, it will make it diagonal or anti-diagonal. Okay, depending on whether it is horizontal or vertical, it will make diagonal, anti-diagonal. PBS, I told in the beginning, it transmits horizontally polarized light and reflects the vertically polarized light. Okay, so you prepare these polarization states, and BS like beam splitter. So it is like polarization agnostic. It doesn't care about polarization. It just like combines all the signals. So all these signals, polarization states are combined and they are sent to Bob through this launching optics. Okay, this is the launching optics combination of lenses. So you have to collimate the signal so that it can travel longer distances. Okay, without further divergence. And then you have to collect here. And this is just alignment laser. Okay, this is another laser we use for alignment, just to check that signal goes to Amba. First you align with this layer, then you send this signal, this quantum signal, to the ball. So this collection optics you collect at the other end, and then you make the measurement. Okay, here again you are doing the random selection of the bases. Here you see half a plate is there. So this is basically you are selecting here diagonal and anti-diagonal bases. Here, this is just PBS, so you are selecting linear basis, horizontal and vertical, because this transmission is horizontal, reflection is vertical. So you know which detector is having which kind of polarization. Okay, you can assign this will be measuring L, this will be measuring V, this will be measuring D, this will be measuring A, so that, and then you have time information also. Okay. So when you go to the field instead of lab, so this setup you make it on a breadboard, optical breadboard. You fix everything on an optical board. This is called optical breadboard. Electronics, you know, similarly for optics, you have breadboards. Okay, holes on a metallic sheet. So you fix all those mounts, optics, and everything, lasers on a breadboard, and then you take to this field and do the experiment. So this experiment is being done by Sarika in the field on the terrace of our building. So we have two cabins here, Alice and Bob cabin, transmitter and receiver. You can see here further details. So this is being transmitted. Okay, this is Alice, and then there is another building in our campus. Okay, which is 100 meters far from this building. So this is being reflected and being collected by the receiver. So that makes it 200 meters free space quantum key distribution. Why we made this arrangement? Because we wanted to show for 200 meters. Rather, we had a project to show quantum key distribution, free space quantum key distribution for 200 meters. But we have only two buildings in our campus which are there. And they are 100 meters apart only. So that's why we have this kind of arrangement. So I told you in the beginning itself, time records are very important. So if Alice is sending H polarized light prepared in horizontal polarized these photons, and Bob is measuring. This is the measurement results, okay? And Bob is uh, recording the counts or observing the counts in each detector. So this detector, which is supposed to get as polarized, that will have maximum counts. Okay, and this counts is order of 425, 450, something like that. That upper. So and this time window of this detector, like regarding the pulses, this is 1 nanosecond, and you collect for 10 milliseconds. this photon. So this is there, and then this very small number for vertical, you can see that. Okay, and then you can see that this delay is very important. You should notice that 689 nanoseconds. So if you calculate 200 meter, how much time it takes for light, it must be approximately this much. Okay, um, because we are not exactly 200 meters. Okay, so and if you deviate even 1 nanosecond from here, this delay thing. Okay, this delay from Alice H polation laser diode to Bob H, that's what it is, this number. If you delay even change it by 690 or 688, you will not get this kind of counts. So time is very important. And then you see there for V, you will have very less. Okay, if you send H here, Alice is sending H, but Bob will not get very less count in V. And if Alice is sending H, Bob will have counts in D, okay, half of the counts in D and half of the counts in A, because horizontal polarized light is superposition of diagonal and anti-diagonal polarization state. H you write as plus A, okay, 1 by root 2 D plus A. That's what you write horizontal polarization in terms of diagonal and anti-diagonal. So if you see almost equal number of counts in detector which is supposed to measure diagonal polarization and anti-diagonal, you can like you can be assured that your setup is working fine. And these two numbers, these counts for diagonal and anti-diagonal detectors, should sum to the horizontal which you are measuring here. Once you ensure that your setup is working fine, you can have this quantum key distribution, or you can have key information. So channel transmission is very important. You have to characterize your channel. What is the transmittivity of a channel? You have to know the detector efficiency. Detector efficiency includes the losses in the optics also. You have to know, suppose you are using weak current pulse, so you have to know the mean photon number per pulse, and what is the repetition rate of the laser also you have to know. Okay, in our case it's 5 megahertz. So once you know these parameters, you can extract the key. And in this case, we have got around 200 kilobits per second average shift key rate. This is shifted key rate. Then you do the error correction and privacy amplification, and you get this kind of secure key rate. This QR parameter is very important. Quantum bit error rate, as I told you in the beginning, R is equal to in terms of like 1 minus H2 EB. So there that EB was the bit error rate, quantum bit error rates. And this has to be less than 11.2. And you can see that here, bit error rate ratio. This is 2.8, okay, 3.3. So it's much below 11.2%. That's how we are having this positive key rate. Otherwise, we can't have this positive key rate. We cannot generate security. I told you that one can have very secure communication using quantum key distribution, but um, all your devices, they are not perfect. Theoretically, it's fine. You can say ki, we are doing quantum key distribution, so everything is very secure. But in practice, our devices will have imperfections. They will not be perfect. Suppose I intend to generate horizontal polarized light, but it may not be perfectly horizontal. I intend to generate diagonal, it may not be perfectly diagonal. My suppose I'm using four lasers. All the lasers wavelength may not be same. Okay, if wavelength are not same, one can discriminate. Okay, compared to one population and another population, and if one can discriminate, one can have information. So there are many imperfections, okay, from source side as well as detector side. Both sides can have, okay, imperfections. So one has to take care, like one has to characterize source as well as detection site. And once you characterize, you know which kind of leakage due to imperfections in the setup, which kind of information leakage can be there, which can be like taken advantage by the you. Okay, because of your implementation, because of your imperfection in the setup or devices we are using, there may be information leakage, and you have to know beforehand this kind of information leakage can be there. And once you have that information during privacy amplification, you take care of that which kind of information leakage is there, and so that you will have secure key. So that's what mitigating the source side channel vulnerability by correcting photon is 6. One can have photon, as I told you, one has to measure mean photon number purpose. Okay, so how do you measure mean photon number purpose? Generally, you measure you have a photon detector. Okay, and suppose you are sending 10 power 6 photons and per second, that's the rep rate, you know. And then you measure measuring photons, this is the channel transmittivity, and you are measuring 10 power 4 photons. So if you divide, suppose I say channel transmittivity is 1, here rep rate is 10 power 6, and you are measuring 10 power 4 photons in 1 second at your detector. So average, what is the mean photon number? 0.01. If it is 10 power 5, it is 10 power 6, and transmittivity is 1, perfect transmission, so it will be 0.1. So this is the way you measure in general this mean photon number purpose. So you use only one detectors, but one can have, in principle, as I told you, we are preparing in BBT4, we are having 4 correlation states and we are using 4 detectors. So before doing the QKD, you can have mean photon number purpose also you can characterize very well. Instead of one detector, you use 4 detectors for characterizing the mean photon number purpose. So if you use 4 detectors for characterizing mean photon number purpose, you see that you have better estimate of mean photon number purpose. And if you're using this single detector for calculating mean photon number purpose, that can lead to the information leakage. By you can see that difference when you're using 4 detectors and one detector, you mean photon number purpose we are measuring. So this kind of error is coming, and that error is increasing as you increase the mean photon number purpose. Okay, so, and that error can be exploited uh, by the Eve to collect the information leakage. You see, this is the information, mutual information. This is mutual information between Alice and Eve when you are using this second method, and this is mutual information between Alice and Eve when you are in the first method. So you will see this is increasing. Okay, mutual information difference is increasing, and that can be exploited by the Eve. So this is like preparation stage itself. I mean, photon number per source side, but source side, as I indicated, I mentioned earlier, you are using different laser diodes for preparing these pollution states, and they may have different wavelength, they may have different pulse width, they may reach at different times and the detector. So all those problems are there, so that also need to be characterized, and mutual information has to be calculated for Alice and Eve because of these imperfections. Which kind of information leakage is there, or what kind of information Eve can extract because of these imperfections. And you can see that this is like different way laser diodes are having different wavelength. They are having different pulse widths, arrival time for laser diodes at a particular place is different. So all those things, and then polarization is different. Even this shape, mode shape is different. Like they are not perfectly Gaussian, and all are different slightly from one with respect to other are different. So all this information like can be used by the Eve Using this information, basically you can discriminate between polarization state. Okay, and so it will lead to the suppose wavelength information, different wavelengths. So it may lead to this kind of 10 power minus 3 bits per pulse. And suppose you are sending like rep rate is megahertz, so 10 power 3 bits per pulse. That's what 10 power 3 bits per second information leakage can be there. And same way, this pulse which is different, that may lead to 10 power minus 3 bits per pulse. Okay, so but per second you are having megahertz in power 6 pulses, so per second you may be losing this kind of information 10 power 3. And this arrival time, same way polarization and spatial mode discrimination, there may be information leakage. And so one has to take it, this is leaking more information. This if your collection optics is not good, you will be losing more information to the EU. So one has to take care of these things, and one has to characterize beforehand, before one starts like doing quantum key distribution for encryption. Same way detection side also can be exploited by the eve to have information. Okay, and that also can be characterized if you are not aligning your setup properly. There is miscoupling between the this fiber and detector, that may lead to the information leakage. And that's what we show here, what kind of information leakage. So here low coupling mismatch, high coupling mismatch you see here, completely different. Here low coupling all are having same. Okay, so if you have this kind of high coupling mismatch, that may lead to uh, cross correlation and information leakage. You see, because of miscoupling you will have information leakage here. And cross correlation is a technique. By measuring cross correlation we estimate this mutual information or information leakage. So this is showing cross correlation here, and here it's showing information leakage. So this mismatch, when you are detecting, so coupling mismatch can have information leakage. So you have to characterize your setup when you do the quantum key distribution beforehand, and what kind of information leakage can be there to Eve. You have to estimate in your setup, particular setup, and you have to take care of it during privacy amplification. That's very important. So we go for like how you do with quantum key distribution using entangled photons. So first, you have to produce entangled photons. I have already discussed this point. You have pump laser. Laser, we can say key, frequency and momentum, or energy and momentum. You can define. Uh, so it passes through this Chi2 second order Nollier crystal, and because second order Nollier crystal, it breaks one photon into two photons. One is like signal and idler. That's the convention to label them. Okay, these two photons, and this is like momentum. This is frequency, angular frequency. Omega is angular frequency. And as I told in the beginning also, it follows conservation of energy and momentum. And you can see that this pump photon breaks into two photon, that follows like energy conservation. Okay, and it is like momentum conservation also. This is pump photon, and some of this momentum is equal to pump photon momentum. And this is called phase matching condition. Okay, so crystal has to be like cut at particular optic axis should be aligned to a certain angle. Okay, compared to the laser propagation direction, then only you will have this kind of phase matching condition. So you can have different sorts of, and a very nice article has been written by Karan, yes, Karan Suman, and Anand Jha from IIT Kanpur, as well as our student Ali and colleagues on this topic. One can go through that. So this is one of the entangled photon source. We have generative, we have developed in our lab, but You should note that this is not the only way to generate entangled photon source. What is the basic? You have to generate two photons which are highly correlated. For that, this is the basic. So for that, you can use any kind of setup. Okay. This is just one of the setups. So here what we are doing, we are taking a laser 405 nanometer laser. This is like we are preparing a polarization state using half a plate, and then it goes through the dual PBS. Dual means this works for 405 as well as 810 nanometer. So here one should know that one can have degenerate down conversion, one can have non-degenerate down conversion, one can have collinear down conversion, one can have non-collinear. Degenerate means both the photons will have same wavelength of frequency, and non-degenerate both will have different wavelength. That's the meaning of non-degenerate. And we say collinear means both the photons will be collinear along with the pump, same direction. All of them will have same direction. That's collinear. And when we say non-collinear, these photons, generate photons, will have different direction. So all those things can be there. You can do all sorts of things using phase matching condition depending on the crystal. Okay. Uh, so here you produce these two non-collinear degenerate photons. So you are having 405 nanometer, and these photons are produced having wavelength of 810 nanometer, and they are non-collinear. They are going in different direction. You can see that. Then you do the polarization correlation. So you see with the polarization, these are the polarizing elements. Okay, linear polarizers, and then you look at the correlation in polarization. And if you see the correlation in polarization, you say they are polarization entangled. And these filters are there to cut out the like ambient light or stray photons. It allows only signal to pass through to go through the detector. Okay, and these are the single photon counting modules or single photon detectors, and they are coupled to the fiber so that only intended signal goes there. And even then, and before that, we use filter to cut out the stray or noise photons. And then we see this correlation. Suppose this you fix at horizontal and you keep on rotating, so this will be this kind of curve it will follow. Suppose you fix this at vertical or diagonal, then you will find this kind of curve. Okay, this is kind of interference and interference curve, and this correlation thing, so that's why it's interference curve. And some at one point they are highly correlated, at another point they are not correlated. Okay, that's what it's showing. And visibility, if this visibility of this interference curve is more than 71, you get like entangled photons. If it is less than 71, you don't get the entangled photons. Visibility of this curve, okay, you can ensure that you are having entangled photon. You can do further characterization of this entangled photon source by measuring the by doing the quantum state tomography. Means what is quantum state tomography? Basically, you are reconstructing the quantum state, okay, which you have generated by making large number of measurements. You know the CT scan, you know, current tomography. So there also you do lot of images you take and then you combine to create the 3D image of the object. The same way here also, quantum state, you make lot of number of measurement and then try to make the quantum state. And if that you can do, and fidelity is like 0.975, means it's very close to 100%, close to one. So what state you wanted to make, you have made almost the same state. Okay, that what it shows, measurement, quantum state tomography. and it's very robust. Like there is very little. It's all along you see this fluctuation. This is for how much? It's very long duration, like so it's 3600 seconds, so very stable. This single photon counts. So that's how you do. And what is this? Like these are the counters. So you do the coincidence counting. So for this, these are the coincidence counts. Coincidence count means when both are having photons at the same time. So you fix the time window, suppose 10 nanosecond. When both are having counts in the same time window, you say this is the coincidence. So that's what you measure, coincidence counts, and from that you get this visibility thing, and from that you can measure the entanglement or Bell parameter. So I'm talking of this coincidence counts. So that's what these are the coincidence counts, and is the coincidence count for different this angles of different correlation settings, polarizer and laser, whatever you say. For different correlation settings, okay, you have coincidence counts you can have, okay, and then from that you calculate the correlation coefficient. Okay, this is the correlation coefficient, like how well they are correlated. If then these correlation coefficients you put into this expression, and if you get, this is called Bell parameter, S is called Bell parameter, and if this correlation coefficient is more than 2, you are having entangled photons, and if it is less than 2 or equal to, you are not having entangled photons. They are not highly correlated as desired by the quantum mechanical principles. So that's called Bell inequality violation, or CHS. CHS is like name of scientists who modified the Bell inequality for experiments. So this is what you get. So by making measurements, coincidence counts, and then correlation coefficients, and then measuring the Bell parameter, you can ensure that you are getting entangled photons, what you wanted to have. So now you can have quantum key distribution using entangled photons. It's very similar to BB84, but here there is no preparation measurement. One party like satellite is having entangled photon source. You can say Charlie, and Charlie is distributing photons, okay, to Alice and Bob. And then there are random selection of bases for population, diagonal, anti-diagonal, horizontal, vertical, and then they make measurements. Okay, then do the shifting like basis reconciliation, both are using same basis or not. Then they get this kind of, then they do the error checking. I told you horizontal, vertical thing, even if you're using the same basis, so you have to do the error checking. Then finally they get the, so this is classical channel to share the information regarding time and all those things, or time tagging. And this is the quantum channel because you are sending photons, which are the quantum entities, as I told in the beginning itself. Um, so this is the arrangement. Here you have entangled photon source, okay, and one photon is going to LS, another is going to Ba. So these two photons are there, and one is going to Ba. And then both the parties make measurements in polarization. Okay, both the parties are making measurements, and they have time information, and from that they can develop the key, and that key can be used for encryption and decryption. Similarly, you can have breadboard on, you make the setup and do the measurement in the field. Here you will notice that we are having the two boards in the same room, and you will see the effect, its effect when we are doing the key measurements or measuring the coincidence count. So you see, this is the detailed schematic. This is one building we call Thaltej, new building Thaltej, where our lab is there. This is terrace of that, where we are having this cabin. Then we have this building wall here. Some wall is there, boundary is there, and this is like 16 point. This is like if you do the reflection by keeping one reflector here, this is 735 meter, 17.5. So this is 35 meter. And if we keep this reflector here, this is called astronomy building, old building. So if we keep, you can see that there is no other building in this area. Okay. So this is 100 meters and this reflection makes it 200 meters. So that's what we do. This is Ellis and Bob. This is the reflector here. And this is the entangled photon source. One photon goes to Ellis and another to Bob, and that's what you get. And then you make the measurement on these two photons, and you see that even after 200 meters they remain entangled. You measure the Bell parameter after measuring the coincidence counts, and these outer lines are confidence interval lines, 98% confidence interval lines. And this middle one is like theoretical fit, so very good. We are getting very good results, and we can verify that they are still entangled after 200 meters. We are getting very good visibility showing that they are entangled. And then using this time information, time delay, as in the earlier case for BB84, we can have key, we can extract the key. So since we are measuring, since we are producing HH plus BB kind of entangled state, okay, you can have like, this is one of the Bell states, HS plus PV. You can have four Bell states, but here we are producing HS plus PV kind of Bell state. So HH, these diagonal elements will contribute to the key. H can be written as HS plus PV, can be written as DD plus A also. So this diagonal thing will give you the key. And same way, you have to characterize the channel, detector efficiency, everything. And you get less number of keys here because entangled photon rate generation is not at the same rate as like repetition rate of laser, which we're using for peak current in earlier case. So here you have less key. It's 4.5 kb instead of 200 kilobits per second. And after privacy amplification, error correction, that reduces to 1.7 kilobits per second. And here again, you have you can see that Cuber is quite low, 4% again, less than 11.2. Then somebody was asking the atmosphere, that atmosphere will have losses when photons propagate from satellite to the ground. So they will have losses, and depending on atmospheric condition, you will have different kind of key rates. That also we have verified. Okay. And very interesting that atmospheric parameters, they follow the key rate. Okay, so if you have key rate information, you can extract information about the environment also. Okay, because environmental conditions, they follow the quantum key rate. Okay, what we are generating. So once you have free space quantum keys, using free space, you have developed quantum keys for encryption. You have to integrate it with a fiber-based quantum key if you want to have quantum network. Okay, so that's what we have done along with C dot. You can see that like here PRL Alice, we are having free space thing. So Alice and Bob are there. So you develop the key. Okay, K2, both are having key this K2, and then you have like a fiber based key is K1, and this is like secure node. So you here, this is K1, this is K2. You do the jar operation, K2 jar K1, and now this do the another this jar operation, K2, and then you will have K1. So now both here are having the same key. So from this end to this end, this is the network, free space and fiber network. So from this end to this end, you can have secure communication. So that's what from like what is happening at PRL. We are doing more. These are the already published results. Okay. So now let us discuss the globally what's happening in this field. So as I mentioned in the beginning itself. China is the leader in quantum communication, and China is the only country which is having satellite for quantum key distribution. Instead of now, they are having more than one satellite, and they are having good number of optical ground stations. In the beginning, they have bigger satellite. Now they have much smaller satellite. Now they have in the beginning they have much bigger ground stations. Now they have made it very compact optical ground stations, and they are planning to launch four more satellites by 2026. And they have already demonstrated quantum key distribution across Asia, Europe, and Africa. Okay, and they are planning to have worldwide quantum computer network by 2030. Their plan. These are the some of the results they have published in all top-notch journals: Science, Nature, Physical Regulators. So they have shown that even after 1200 kilometers, these entangled photons show the Bell inequality violation. They remain entangled. Satellite is here. It is sending photon here, entangled photon one coming here. They are making measurements. They could show that they remain entangled. And then using weak coherent pulses, they could establish the do the quantum key distribution, and that keys which they developed using this quantum key distribution, they could do the secure video conferencing across continent, across Europe. Like this is Vienna, and this is in Shanghai. So that's what across the Asia and Europe. Okay, they could do the quantum key distribution long distance. Okay, and now they have established like quantum key distribution channel with South Africa also. But along with China, there are other countries which are active in this field. Rather, this Italy, they were the first to publish paper on this quantum key distribution using satellite. They show the feasibility. They didn't do the quantum key distribution. They just showed the feasibility. Okay, that one can do that, um, and publish the results 2015 physical regulators. Japan has done, but that satellite didn't work for a long time. They had very compact. They had very compact payload as well as optical ground station, and but their result was published later. Although they launched satellite earlier than China in 14 itself. Okay, instead of 16, China launched first satellite in 16, but the results were published later than the Chinese. So Japan is also very active, and same way Germany is also very active. They could demonstrate like from flight quantum key distribution, flight at the height of 20 kilometers. They could demonstrate the quantum key distribution in 13 itself. Okay, that's Germany using optical ground station and payload in the flight. And Singapore is also very active. They have sent like quantum payload satellite, and shown that it's working in the space. They have tested like entangled proton source is working fine in this space, and now they plan to do the quantum key distribution using ground station. Canada is very active. They have planned for this uplink as well as downlink. So uplink means when you are sending signal from ground to satellite, and downlink when you are sending signal from satellite to down ground station. So both they are planning to do. Let's see when they will be able to do. And USA has also started effort in this direction. They have many projects running, and then UK is also having projects. Abu Dhabi is having ground station, and they are ready to offer their ground station to any of the countries uh, which are interested in quantum key distribution. Singapore, Israel, all of them are very active, although still they don't have any successful quantum key distribution demonstration using satellite. So these are the progress we have made while working on the quantum key distribution. We have published we have done BB84 quantum key distribution as well as BBM92 using entangled photons. We have characterized like mean photon number to check like information leakage from source side, and then other source side interaction side. We have characterized the setup and we have published these papers. Then we have developed a new protocol that I have not discussed because we are running out of time. So, and that new protocol gives much higher key rate compared to BB84 and the decay state protocol, and that also has been published. Okay, and certainly for entangled photon based quantum key distribution, we have made entangled photon source. Without that, you can't do that, and we have done that. Okay. So we are still working in this area. We have device independent quantum random number generator, and we want to have device independent quantum key distribution also. Okay, and we are working in CVQKD also, as I mentioned in the beginning. So this is the progress, and this is the future plan of work at PRL. We want to study the effect of turbulence, atmospheric conditions, and how to mitigate it using adaptive optics and machine learning and AI. That can be done. Okay, that's how you make your ground decision compact. That's what China is doing. And then you can simulate conditions for uplink and downlink and check which is better in which condition. And then develop a device independent quantum key distribution protocol. That's what we are working on. And then we want to have entanglement swapping. Somebody was talking of entanglement swapping and quantum teleportation to develop quantum commission network based on entangled photons. We are very good at making structured light, and that we want to use for robust and secure quantum key distribution. And guys at PRL, they are working on photonic quantum computing, and we want to have this photonic quantum computer. I bet for quantum photonic based photon based quantum computer, because if you have this quantum computer based on photons, you can integrate this computing and secure communication very seamlessly. And that's why many countries and companies, they are working on this photonic quantum computing. Genado in Canada, Sai Quantum in USA, and they have very big setup. So Orca in UK, and there are many other companies in different countries which are working on photonic quantum computing. So that's what. So, and we have found a startup, and that is providing quantum science and technology kits to understand what is entangled photon source, what is single photon source, and demonstrate quantum key distribution, real quantum key distribution, not analogy. So I am working along with my student in this company, and we are developing, and institutes are now gradually asking for that. Let's see how many institutes will be taking this advantage of the kits which we have developed. Okay, thank you. You can ask questions here.
Okay, thank you, Professor Singh. There are few questions which we can take possibly. So the first question is, what would be the power levels used to transmit and receive the photon? How can we relate them with distance between transmitter and receiver?
Power level, as I told, it has to be, if you're using weak current pulse, it has to be very small. Mean photon number per pulse, it has to be less than 1. So you don't require very high power when we are doing quantum key distribution. And when we say single photon, so at one time you have single photon, entangled photon also 10 power 6, 10 power 7 photons per second. So power levels are very less. Okay.
Okay. The second question is how the frequency of source affects the communication.
Frequency, if you are doing free space or fiber. Suppose you are doing favored wavelength, like minimum attenuation wavelength is communication with 1550, okay, C band. One can use O and L band also, okay. So you have to select the wavelength which will have less attenuation in fiber. Same way, like atmosphere. So many of the wavelengths are absorbed by the water vapor or in the atmosphere. So you have to select a wavelength which will have minimum absorption, okay, which is transmission window, which has maximum transmission in the atmosphere, and which have less background also. That those things. So accordingly, it's not. It depends on like which frequency. This quantum key distribution will depend on which frequency you are selecting, a wavelength you are selecting. So you have to be careful when you are selecting which kind of wavelength you are selecting for communication, depending on fiber or free space.
Okay. So next question is there any relation of communication accuracy on spectral width of the source?
Spectral width of the communication accuracy, if you are doing frequency entanglement, then only there might be issues. And but when you are seeing polarization, there it will not affect the polarization entanglement, or so it will not have effect on polarization thing, okay, if it is frequency there is some
All
width.
right. So next question is we know nowadays satellite-based quantum communication such as teleportation is being researched. Now, as we know, teleportation is the reverse of dense coding. Is there any progress in this direction with respect to satellite-based quantum communication?
China has demonstrated this quantum teleportation. Other than that, using satellites, nobody has demonstrated quantum teleportation. But quantum teleportation for longer distances, like kilometers, has been demonstrated in Europe and USA, using fiber as well as free space. Not many
Okay.
experiments. There are very few experiments, but it has been demonstrated.
Okay, so the follow-up question is, are you saying at last all measurements are subjected to Bell non-locality test? What about Hardy's non-locality in such cases?
RD localities for macroscopic systems, just to show the quantum behavior. But when we are doing macroscopic, like photons and all those things, we are using. So we are mainly interested into this Bell inequality, and that also when you are having entangled photons. Okay? If we are using a single photon or weak current pulses, you need not to bother about Bell inequality. Okay, only when you are using entangled photons for this quantum communication or quantum. So you have to verify that they remain entangled using entangled photons only. That's why you measure this Bell inequality. So when you are using this photons thing, you don't require this Hardy's inequality analysis. So Bell inequality is good enough,
Okay, so
at
this
least for
is
bipartite system. Yeah, yeah. When you're
all right.
using just two photons, yeah.
Okay, so this is more of a general question, not a technical one. Why is India lagging behind China? What are the barriers?
China, India, because India started late, and the kind of investment China is having, we are very minuscule compared to that. You can guess from that, China is just one lab is having more than 10 billion investment, $10 billion. Okay, forget this national quantum initiative or national mission there, quantum. That has more than 10 billion. Okay, investment. Just one lab is having more than their one lab for quantum information, quantum. National Lab for Quantum Information, thing like that. That name is there. So just one lab is having more than $10 billion investment. And India National Quantum Mission, we have less than 1 billion for whole of the country. Okay, and so and they started earlier compared to us. So certainly we are behind compared to
Okay,
China.
so the follow-up question to this same question is, I have noticed that the young minds working in CDAC and like are lacking funding and some are confused about what to do and how to proceed. I think some gaps are there which needs to be taken care of. What are your comments?
Comments, we have to train our human resource because we started late in this field. We have very we started late, so we don't have much trained power. Even if even money and all, we don't have sufficient hands to work on this kind of technology. So we have to train faster. Okay, students, our workforce, prepare the workforce, and then there should be sufficient funds. Okay, to carry out the project. So we both things should be taken care of. Funds should be there, and along with that, there should be trained manpower which can use funds properly to the develop good quantum technology products. Yeah, useful technology based on quantum technology.
Okay. Okay. So the next question is which QKD protocol China is using?
Till date, China is using Decay state protocol till now mainly. Okay, that's what they're doing, Decay state protocol.
Okay. So the next question is, could you please elaborate on device independent QKD protocol?
Device independent protocol, basically they use entangled photons. Okay, and because it's based on entanglement, so if you can verify that you entangle, it doesn't matter which device, from which device it is coming. Okay, so it becomes device independent. There are certain more conditions, but basically you have to use entangled photons if you want to make a device independent quantum key distribution, because it is related with that condition, not depending on which device is producing. So you are measuring photons and they follow that condition, like they're entangled. So it doesn't depend from which device it's coming. So that's how it becomes device independent.
Okay, so next question is two photons have two different wave packets after entanglement. They may have same wave packet. So how we distinguish between these? We receive two different photons or the same photon?
Same photon and different photons, if they interfere, suppose that's quantum interference, no? That's correlation we measure. You have to basically measure correlation. If they are the same photons, there will be very good correlation. If they are different, there won't be any correlation. So you have to measure the correlation. That's what we do. Even classical also, at that you have to do in quantum also. You have to check the correlation, and that correlation you can do by measuring. You can find out whether they are correlated or not. So if they are correlated, they are the same. If they are not correlated, they are the different. So this correlation measurement can be done. There are techniques. Okay, that can be done. I have shown already correlation measurement. Without correlation measurement, you can't verify the entanglement. So similar kind of correlation measurement you have to do. If they are correlated, they are same. If they are not correlated, they are different.
All right. So in free space communication, almost every environmental parameter, temperature, humidity, turbulence affect the communication. How all these
Hmm.
parameters would be controlled in single photon at transmitter and receiver end?
So you can't control the parameters there. Atmosphere is there, whatever it is there. So depending on atmosphere, you will have different key rate. That's all. Atmosphere parameters you can't control. You can control your generation rate and measurement rate. That's all you can control. At the protocol we're using, you can change the protocol which will have much more efficient key generation rate. So you can change those things, not atmospheric parameters. So and if you have higher entangled photon generation rate or higher single photon generation rate, you will have higher key rate. There will be losses in the atmosphere. You can't avoid. Or even if you are using fiber, there will be losses. So you can't avoid.
All right.
Uh,
So
am I? This is the answer. It's fine. Or you want to have more some other information?
I mean, the participants probably, if you want to follow questions, you can post it on the chat window, or if you're
Yes.
satisfied, it's okay.
So any other question? What is the other question?
The other question is, what are the research possibilities in BB84 protocol connect with 5G communication security?
BB84 protocol is a good protocol, but generally it has to like Decay state protocol is the extension of BB84 protocol, so that's what one has to use. But and this is the protocol being used currently. What are the commercial implementation is there? basically request protocol is being used. That is extension of BBT port. But here, as I told, this is trusted network. Okay, trusted node. If you want to have, you have to trust that because key information is there. When you say prepare and measure, key information is there with the nodes, and you have to secure the nodes. So this is trusted node network. If you want to have untrusted node network, you have to have a network based on the entangled photons. Okay, that will give better security. And so we have to go long way. I always say just securing a few nodes communication, secure communication between few nodes is not going to make any sense because we are moving around. It has to be a global communication network. I may be here, I may be after 1 month, maybe in Australia, maybe somewhere in Germany after a few months. So you have to have global network, or I may be in Delhi instead of Ahmedabad. So unless until we have global network, it doesn't make much sense. So for global network, it has to be based on entanglement. Okay, fiber network if you want to have. So it has to be entanglement based because there you can do. So and quantum repeater is important if you want to have long distance quantum network where you can store the state and you can make purification or distill the state. And so quantum memory is required. So many things are required. Still, it's not like commercially available. This kind of network with all the devices are not commercially available to develop this global quantum communication network or quantum internet. So that is the ultimate goal, this quantum internet, where all the quantum computers, all the secure communication, all will be integrated. So that will be the quantum internet. Yeah.
Okay, so there is this follow-up question from the same participant who asked the question related to the weather parameters related to the single photon. So the
Mm.
question is how we will control the noise due to these parameters.
You can't control the noise. You can have like whatever noise is coming. You make measurements. By making measurements, you can have like your signal. Okay, so um, you have to cut out the noise at the measurement level. Okay? You have to take care of the noise at the measurement. That's the only thing you can do. So at measurement level, you take care of the noise.
All right. Okay. So thank you, Professor R.P. Singh, for your valuable time and basically accepting our invitation to be speaker in this FTP. And this is actually the 16th day of this quantum communication where participants have been learning theoretical aspects of quantum communication. And today probably they have seen the practical demonstration. And uh, uh, that I participants must have been motivated to this area. Then anyone wants to hear. Thank you.
Okay, thank you. Can I leave now?
Yes, yes, you may leave. Thank you.
Okay.